In this video, we are going to learn about Green's theorem. So this is one of the big theorems of vector calculus, and there's two parts to this. So what we're going to talk about here is called the Flux-Divergence Form. So the theorem says, let F be a vector field in the xy plane. So it has this I hat portion, this j hat portion, but no k hat because it's just in the xy plane. And let C be a simple closed curve that encloses a two-dimensional region R. So if I draw a picture, we have this closed curve, which means it starts and ends at the same spot, and I'll call that C. And the region within, I'll label that R. If our vector field has continuous partial derivatives throughout the region, so no matter what point I take within the region, if I take the partial derivative of either of these components, I need those to be continuous at any point within the region. Then it turns out there's a really nice formula for the flux of the vector field. Remember, the flux is telling me the rate at which, if our vector field is describing, let's say, a fluid, the movement of some fluid in the plane, the flux tells me the rate at which that thing is crossing this curve. So I need, in this context, the curve to be traversed counterclockwise. So I'll draw some direction arrows. I'm going around it counterclockwise, which induces this orientation where the normal vector, this unit normal vector, points outward. So I'll draw it at a couple of points. So this vector of length 1 perpendicular to the curve, that normal vector, I'll draw it at one other spot. So I'll draw it here. I got another normal vector. Okay, so this line integral is telling me the flux of this vector field across that curve, the rate at which this, if it's a fluid, is crossing this curve on this boundary. And what Green's theorem says is, it turns out that's equal to a double integral over that region R, where you do the double integral of the divergence of F. Okay, and what's the divergence of F? Remember, another way to write that is, you write this del symbol and you dot it with the vector field, where the del symbol consists of taking partial derivatives with respect to each of the variables. And because I'm going to dot it with the vector field, I'll take this x component and I'm going to apply the x partial derivative to this. So that'll give me partial of m with respect to x. And the dot product means, well, now I'm going to start to add up things. Then I'll do the y partial derivative applied to this y component. So that'll be partial of n with respect to y. And here, because I'm just in the xy plane, there's no z, so I stop there. So that's my divergence. And then my notation for a double integral is I write dA. Remember that conceptually divergence is, if I take some point, the divergence is measuring the rate at which this fluid is passing through that point. So what this theorem is saying is, when you look at this double integral, when you look at this whole region and you kind of take all those divergences within the region, that somehow, kind of everything within in the inside kind of cancels, and all it ends up giving you is what's happening on the boundary, the rate at which this fluid is crossing the boundary. Okay, so how do we prove this thing? So the idea I'm going to use is, so flux is this line integral of our vector field dotted with the normal vector. And we've seen that with a line integral, I can express it as this limit of a Riemann sum. So if I have this curve, some curve, whether it's a closed curve like I have in this picture, or generally just a curve that starts somewhere and ends somewhere, I can cut up into a bunch of tiny pieces. And then on each of those pieces, I can approximate the flux by taking some test point, figuring out what the vector field is going to give me at that test point. That's what this Fi is. And then also drawing the normal vector at that test point. That's what Ni is, this perpendicular vector. And that is going to get multiplied by delta S, the length of that piece. Okay, so right, I can express this line integral as this limit of a Riemann sum. Okay, so how do we prove this thing? So let's say that this right here is my curve. I'm going to label that boundary curve C. and I'll label the region within R. So, okay, so let's say that I have this vector field F, that C is the simple closed curve. I'm going counterclockwise around it, and it's enclosing this two-dimensional region R. If I want to find the total flux across this curve C, instead of doing it with this line integral, let's take another approach. What I'm going to do is I'm going to chop up the region R into rectangles. All these rectangles that I've drawn in here. And I'll shade in one of the rectangles. Let me shade in one of the rectangles. And that rectangle, you know, it has this width and it has this height. The width is in the x direction. The height is in the y direction. So I'll call the area delta A. And delta A will be that little width, delta x, times that little height, delta y. All right. And next up, what I'm going to do is, let's start off by approximating the flux across just one rectangle. Eventually, we'll see that when we put all the rectangles together, somehow a bunch of stuff will cancel out, and we'll only be left with the stuff on the boundary. Okay, so let's start off with just one rectangle, though. So I'm going to take that shaded rectangle, and I'm going to draw it a bit more zoomed in. So let's draw this shaded rectangle more zoomed in. So I will enlarge it. So that rectangle, okay. So we got something like this. And I'm going to label some points here. Let's say that this x coordinate is x. Let's say that I'll label this y. And you know, I had called this horizontal distance delta x, so I'll keep doing that. I had called that vertical distance delta y, so I'll keep doing that. But if I do that, then the x coordinate here is x plus delta x. And the y coordinate up here is y plus delta y. And I'm going to orient this rectangle by going counterclockwise around it. So I'll draw these direction arrows. And when I do that, it induces this orientation where the normal vector is going to point outwards. Because remember, as I travel along the curve, the normal vector should be to the right. And if I go counterclockwise, that'll be to the outside. So I'm going to draw a normal vector here. Normal vector to the top is straight up. Normal vector on the left is straight to the left. Normal vector for the part on the bottom is straight down. And the normal vector to this point on the right is straight to the right. Okay, so these are all normal vectors, all these vectors that I've drawn in. Okay, so what I want to do now is find the flux across each of these sides. So let's start off with the flux across the top. And I'm going to approximate this. So I'm going to use the idea that I have from this Riemann sum by taking some test value, finding my vector field at that test value, dotting that with the normal vector, and then multiplying that by the length of that curve. So for the top, what I'm going to take as my test value, my test point, is this point on the left. So I'll take that point, plug it into my vector field. So the x coordinate's x, and the y coordinate is, I realized I wrote something wrong. Instead of y plus delta x, this one should have been y plus delta y. Let's fix that. Y plus delta y. Because that's my y value, y plus delta y. And now I need this normal vector. Well, it's pointing straight up, and it has length 1, so that normal vector should be j hat. So that's my normal vector. And then that should get multiplied by the length of that curve. And the length of this, well, that's just delta x. That is just delta x. Okay, so next up, I got to take this dot product. So the vector field, for that, I just take this point and I plug it into my vector field. So it's going to get plugged into both of these components. Remember, j hat is just the vector 0, 1. I'm going to dot that with this vector. When I do that, I'll get 0 times this m portion, that goes away, and then 1 times this n portion. So that just leaves me with the n portion. But where I'm now plugging in this point, so I'm plugging in x and then comma y plus delta y, and then the delta x, well, that is still there. Okay, so that's an approximation for the flux across the top. If I want to now do the flux across the bottom, again, I'm going to do an approximation. So I'll pick some test point on that bottom portion. I'll just pick this point in the bottom left corner. So I'm going to plug that point in to my vector field. So I'm going to be plugging in the point x comma y. The normal vector, because it's pointing straight down and it has length 1, that normal vector is negative j hat now. Okay, and so negative j hat, that's 0 comma negative 1. That has, I got to dot product that with my vector field. So when I do that, when I dot product 0 comma negative 1 with my vector field, well, 0 is going to multiply this m portion. That'll go away. Negative 1 will multiply this n part. So that'll give me, it'll give me negative, I got to put a negative sign in front, negative n. And then I got to plug in x comma y. Oh, and I forgot to write the length of that curve. The length of this bottom is also delta x. So doing the dot product, I have this, and then that delta x, well, that's still there. Okay. All right, so now if I add these two together, the top and the bottom, I notice both of these have a delta x, so I can factor that out. And then in brackets, I'll have that first n term, and then minus this other n term. So now I want to observe something. This thing in the brackets kind of looks like a definition of a derivative. In fact, it would be a definition of a derivative. Actually, it would be very close to a definition of a derivative if I had a delta y on the bottom. But I can't just randomly put a delta y on the bottom and divide by it unless I also multiply by it. So let's do that. I'm going to divide by delta y, and to balance that out, I also multiply by delta y. And once I've done that, now this fraction is, it's almost a derivative. It's almost a partial derivative. So I'm going to say it's approximately equal to, and because it's the y coordinate that's changing, it would be the partial of the function n with respect to y. And then delta x times delta y, well, when I multiply that base times that height, that's giving me the area. That is giving me the area. That's delta A, right? We said that earlier. Okay. And so this isn't exactly the partial derivative. To make it exactly, I would need to do a limit in front, and later we will. But for right now, for our purposes, it's an approximation. Okay. So if I do similar steps to the two sides, the left and the right, and I add up their fluxes, I'll get something very similar to this. It turns out that we will get the partial of m with respect to x. So the partial of this m with respect to x times delta A. I'll leave it for you to try that as an exercise, but it turns out we'll get this. So now if we add both of these together, this is the top and the bottom, this is the left and the right. They both have a delta A, which I can factor out. So what that'll leave me with in parentheses is partial of m with respect to x plus partial of n with respect to y. Oh, this thing might look familiar. This is the divergence. This is the divergence of f, right? Or sometimes we notate this by writing our del symbol dotted with f. Okay, so this is nice because somehow when I'm approximating the flux around a rectangle, it's actually quite close to this divergence term. Somehow a divergence is kind of popping out when I do that. So, okay, so far what I've done is I've approximated the flux on one rectangle. And I said what I'm going to do is now sort of do it on all the rectangles and add them together. And there's going to be a bunch of cancellation. So why? Let's do that. So now let's sum the flux over all the rectangles. So when I have two adjacent rectangles like this that share this boundary, I'm going to label the one up top C1 and the one on the bottom C2. And it turns out that when you add the two fluxes that I have here, you get the same thing as if you had erased this boundary and you just made one bigger rectangle, which I'll call C. So why is that? In this rectangle up top, if I draw a bunch of normal curves, so the normal to the top, that is like this. My normal on the left, it would be like that. On the bottom, it's pointing straight down. On the right, it's to the right. And let me also draw the normal vectors to this bottom rectangle. So on the bottom part, it's pointing down. On the right, it would be pointing to the right. On the top, it's pointing up. And then on the left portion, it's pointing to the left. Okay, so when I add up the fluxes of these two things, well, this part right here is the exact same curve. I've just separated a little bit to make it look to distinguish between the two rectangles, but it's the same exact boundary curve. So when I'm calculating the flux on this portion, for the bottom rectangle, I'm orienting the normal that way. So I want to know the rate at which this fluid is passing through that curve going that way. For the top rectangle, the normal vector is oriented this way. So I want to know the rate at which this fluid is passing through that curve going that way. So when I measure that for this top rectangle and for this bottom rectangle, those are going to cancel out because it's the exact same curve, but I'm just thinking about the normal vector in exact opposite directions. They will cancel, and that's why I can ignore that side. So the flux across that first rectangle added to the flux across the bottom rectangle equals the flux across just this rectangle with those two things combined. So if I keep combining the rectangles like that, all the sides that are shared by two rectangles, they will cancel out. And you're just left with this sort of boundary region, which is jagged based on whichever rectangle sides survive. But to make it exact, we take a limit. We take a limit as that delta A, the size of the rectangle, the area of the rectangle, approaches 0. So when you do that, this portion, my approximate flux, will give me the exact flux on my boundary curve. That is what this is. And on the flip side, we've said, oh, we've been approximating this and getting terms that look like this. Divergence times delta A. Well, that, when we're adding those up, that'll become a double integral over this region R, where I put my divergence in the integral. So the partial of m with respect to x plus the partial of n with respect to y, that goes in the integral. And then that delta A becomes a dA. And that right there, that is Green's theorem. We have just proved it. Okay, so in the next video, we will do an example where we use this. And we'll see how it can take the task of computing one of these things, either the left-hand side or the right-hand side, and drastically simplifying it. Because instead of doing the left-hand side, I might convert it to the right-hand side, and it might be drastically simpler.